as Sydney said, I'm going to talk today about some of the things that we've been doing at Mellanox, advancing the capabilities of in-network computing. So the idea behind the in-network computing is to make effective use of data wherever it's present in the system as part of the simulation. And so instead of depending on all computing being done at the endpoints and bringing data to the endpoints to be able to process it, what we try to do is think of ways that the data can be manipulated on the fly and be processed before it reaches the endpoint and as it moves. So there are several advantages to doing that. One, it decentralizes the computation, and so computation can be more efficient. And I'll give some very specific examples here as to what that actually means. And the other thing that this means is data can be processed as it's moving through the network, basically at network speed. So you can set up a very nice pipeline where you aren't waiting for data to transfer from one endpoint to the other endpoint and then do something with it, but you're processing it as it goes through the network. And so the challenge here is to find the sort of motifs that are usable, that are frequently used by apps and can really benefit from this sort of optimization. And so there are some that are very natural in HPC. Those, for example, that depend on using communication libraries like MPI or SHMEM. So they're very easy targets for optimizations. And in other areas, it takes a bit more effort to try and figure out what sort of patterns could be useful for the applications. So the goal here is really overall to reduce time to solution, not just to process data on the fly for the purpose of processing it on the fly, but really to get overall speed up in terms of the end application. And so, while doing computations based only at the endpoints, latencies for example, tend to be, or the overall time it takes to do a certain computation tends to take much more time than it does if you can take advantage of processing the data as it's moving. So collective operations is one of the things I'll talk about. It's a very natural target, and there one can easily reduce, or one does reduce the latencies for these sort of operations significantly, and I'll get into numbers in the presentation. So this is really the goal, is to make better efficient use of the system and speed up overall application performance. So currently, these are ideas that have been going into production. The use cases I'll talk about here are use cases that were developed, are capabilities that were developed as part of the Coral program for providing Oak Ridge and Lawrence Livermore with their next big systems. The capabilities are we have four classes of families that instantiate these capabilities. These are our host channel adapters, which have several capabilities, compute capabilities within them, or more than just compute capabilities, offloaded capabilities. So there's been mention multiple times of the RDMA capabilities. There's a technology called Core Direct, which lets you synchronize between independent flows and lets you build more complex flows that are useful, for example, for collective operations. There's hardware tag matching. This is one of the capabilities that's been added for Coral. And we've also added the ability to put user-accessible memory on the HCA adapter itself. And so for data that, for example, that's accessed by multiple endpoints on the network, so to reduce latencies. The switch side of things, the quantum line of switches. We have Sharp version 1, which does reductions on small data, and then Sharp version 2 is coming up soon that removes the limit on the size of the data that can be reduced in the network. We also have our Innova line of cards, which provides programmability as a bump on the wire currently, as well as an SoC that includes on the same device both ARM cores and the network card itself. So the examples I'll talk about today focus really on the capabilities in the HCA and in the switch. So the line of chips that are coming up now that or this year that will instantiate these capabilities and have enhancements to what we currently have are the HDR devices at 200 gigabit per second. It includes our switch chip, as well as our host channel adapter, the ConnectX-6. I'll provide a few details about these devices. First of all, the switch chip. As I said, the device is an HDR device, 200 gigabits per second. The number of ports on this device that go at the HDR rate, at the 200 gigabit per second rate, is 40. So this is up from 36 that we have in current EDR devices. However, one can also use this switch to switch in a non-blocking manner 80 ports of 100 gigabit per second, are called HDR 100. And which means from a system perspective, you can build modular switches with 800 ports of 200 gigabit per second bandwidth, low latency, same latency to all ports, as well as 1,600 ports if you're running at 100 gigabit per second. So it really depends on what you need in terms of capabilities as to how how one uses this switch. Throughput, it's a 16 terabyte per second device. Latency is still the lowest in the industry, under 90 nanoseconds between between any ports, two ports on the switch. And it supports up to about 15 billion messages per second. The capability that I talked about that's supported there with respect to the in-network computing is the Sharp technology. This is what I'll talk about briefly and go into detail there. So this is reductions within the network. It supports flexible topologies. So Mellanox is agnostic when it comes to topologies. We support what users want to use. It also has some advanced adaptive routing capabilities. So and so we're starting to get very, very good network utilizations, even under adverse network patterns. The HCA device itself also is a 200 gigabit per second device. We talked about the ability to run it also as a 100 gigabit per second device, which is the mode that's necessary to use the switch. Of course, it's backward compatible with our other switches. With our other speeds. It goes at lower speeds. Latency remains low, around 0.6 microseconds, measured at the verbs level. End-to-end message rate is either 175 or 200 million messages, depending on which bin the device is taken from. Supports PCIe Gen 3 and Gen 4. It has integrated PCI switch and support for multi-host technologies. So this is a capability for allowing more than one host to use the same HCA. And at the endpoint now, it also has capabilities to support out of order for RDMA operations. So this is one of the ways we get much better network utilization of the system now. This introduced actually in the previous device in ConnectX-5. The relevant portion here for the in-network computing is support for collective operations and tag matching, as well as accelerations for storage. This NVMe acceleration also has been added for Coral. as well as offloading security and network operations. So now getting a bit more into the technical aspects of the talk and talking a bit more about the SHARP technology. The results I'll show here are very, very recent, measured within the last couple of weeks. And so they're the most recent results we have. And so the notion here behind SHARP, for those of you that have heard talks before on SHARP, notice the acronym has changed, the name has changed a bit. The notion here is to take advantage of the ability to compute data as it's going through the network. And a very natural candidate for this, the easiest one to target, are reduction operations. And right now, well, I'll get into what specifically what we support here briefly. So to explain the idea of SHARP, a very, very simple cartoon of a network with, so first of all, a few explanations with switches, hosts. These designate links between the switches and the host. And if you do, for example, you do let's say a barrier, an all reduce or something like that on four processes, or let's call them for this purpose, each process just sits on a different host. A recursive doubling algorithm would look like this. You have an exchange between near neighbors in the first step, so you have data going through the entire, well, going up through several switches and back. It happens in parallel at the first step, and then the second step, again, you have data going up in both directions, and same thing here. So you have data going end to end twice, or going between the edges twice in this system. However, if you build a tree within your network and use the SHARP technology, and this is really what this is intended to do, is you go up to the network once. So everyone is going to the top of the tree, and then the data is distributed to everyone else. So you go up and down. So for small data, this works well. For large data, it has the added advantage is as you go up successive steps in the tree, which this cartoon does not show well. What happens is the amount of data that's going through the network actually goes down. So at every step, you reduce the volume of the data by the radix of your node in the tree, which can be as high as 80, for example. And the added advantage here is it happens at wire speeds. So you've basically kicked off an operation on the host. You've given the network some data. The host is no longer involved in any of the computation. So at this point, the host is involved at every stage in the computation to compute the reduction of the data. You wait, and so here, as the data, you give the data to the network, and you wait for the result. And no more CPU cycles are necessary. So a bit more about about SHARP. So SHARP is a concept. There's a clear delineation between the SHARP protocol and the underlying transport. They are not decoupled. And so, well, you have a network here that's built, with switches and hosts in some random configuration. On top of that network, you build your SHARP tree. And here's an example of a SHARP tree where these red nodes red stars are what are called the aggregation nodes. They're the nodes in the network that perform the reduction on the data. And the blue stars are the end nodes, are the sources and destinations of the data. So notice here that the mapping of the SHARP tree onto the physical topology doesn't have to be one-to-one. So for example, here, the data itself probably flow through a switch to get from this aggregation node to this aggregation node. This is not an aggregation node, so you don't pay the penalty there for latency penalty for operations. However, for good, well, it depends on system topology and the like. For good performance, it's best to map the topology onto the tree. But it's important to note that they're really decoupled, which helps, for example, in error scenarios, because you don't have to develop a whole new set of way of dealing with error scenarios. For Sharp, you get it for free with what's already available in the transport level. A few things about Sharp. So first of all, there are multiple, multiple trees. Trees are used to describe the system, and reductions are mapped onto these trees. So the infrastructure is designed to support any topology, multiple applications running at the same time. So you have multiple outstanding reduction operations going on. And so a lot of emphasis is put in here on how to use resources effectively when you have multiple jobs running. So one of the ways to do this is to support multiple trees. So you can build, make effective use. You can distribute the load of your reduction load throughout your switching network. And each Sharp tree, and as a matter of fact, each Sharp node can handle multiple outstanding operations simultaneously. So Sharp, as I said before, is logical, a logical construct. In terms of the implementation, we've implemented the end nodes to be, or the sources of data to be hosts, and the reduction nodes to be the switches. There's no reason that can't be changed, and as a matter of fact, probably will change. The other, I think I've talked about most of these. So in terms of the current implementation in ConnectX-5 and Switch IB2, there's support for a large number of groups. So you can think of a group as in MPI as a communicator, and I mean it's not exactly a one-to-one mapping, but it's close. Or in SHMEM, you can think of look at your strides through your process, the processes in the collective operations. Those map to a single group. So you can support, if I remember the numbers correctly, it's several hundred groups at a given switch at a given time, and many outstanding operations, orders of hundreds at a given time. The goal here, again, is to, as I mentioned early on, is to accelerate application performance, and in this case, to offload several of the reduction operations. So barrier, if you think of barrier as a reduction with zero payload, 0-byte payload. You have the reduce and all reduce that map well onto MPI and SHMEM. I should make it very clear that there's nothing MPI specific about the implementation. These are just natural candidates for it. As the size of the data that's supported in a single reduction grows, it becomes much more relevant to some of the machine learning environments, where you can do very large reductions at wire speeds. The operations that are currently supported are basically the set of operations that are the full set of operations defined in the MPI and SHMEM spec, with the exception of the multiply operation. Floating point and integer reduction operations are not supported here. The type of operations that are defined are for integers, both signed and unsigned, as well as for floating point data. And the operand sizes, currently they're 32 and 64 bits. With the HDR devices, we were at support for 16 and 128-bit entities. And so the size of the operation there are two types of operations, as I said. One for short data operations, they take a low latency path through the device. And currently, the length of that vector can be up to 256 bytes. That length goes up in the next device. And then in the next device, we also remove the limit for bandwidth sensitive operations. The results are repeatable. You can run it as non-repeatable, but there's very little advantage from a performance perspective to doing that. So the goal here, of course, is to reduce the time of collective MPI collective operations. And so that's done effectively, and the degree to which applications benefit from this is the degree to which two things. First, they use collective operations, and then with any collective operation, the effectiveness of the algorithm also depends on load imbalance in the application. And so here, again, what this allows is increased CPU availability. The hardware is totally asynchronous, so you can literally fire and forget. And it's a very good primitive for allowing overlap of computation and communication. So a bit of data. This is very new data. For those of you that have seen older data, this is better than it was looking before. So for clarity, I selected just a small number of message sizes, two in this case, and showed their performance this as a function of the number of hosts involved in the operation. So a bit about this. These are the red lines represent data size of 8 bytes. The blue lines represent data size of 128 bytes. And they were really selected to keep the data far enough apart so you could see, you could actually notice the performance. This is done with one process per node. I have some slides later on with more than one process per node. And these measurements are taken at 120, what else am I missing here? Yeah, I guess that's it. So the latency is reported in microseconds. And so we have here the 8-byte latency, you can see, is almost constant from small number of nodes up to 128 nodes, going at about 2.5 microseconds, which is about 2.5 times better than a highly optimized 8-byte all-reduce. This also takes advantage of hardware acceleration. So if you're not, in this case, it's hardware multicast. So if you don't take advantage of those features, typically the all-reduce numbers here are closer to 10 microseconds. So this is a significant improvement in performance due to the hardware acceleration. Similar for the 128-byte reduction. The thing to notice here, this jump that you see here is because of the depth of the tree that's being used. The thing that affects, for the small data reductions, the thing that affects latency the most is the depth of your tree. The number of children at each node has some influence, but very small influence on overall latency. And so what this means is as you get to very large systems, latency increases very, very slowly. And so, for example, at a Coral size system, we expect that the reduction for an 8-byte message with only one process per node will be on the order of 3.5 microseconds or so, and that's about 6,000, or on the order of 6,000 endpoints. This is for the same information, but for larger data sizes. So at this, for 1K, 2K, and 4K messages, so you can see 1K, 2K, and 4K message sizes. There are two reasons to separate this data from the previous, from the smaller data. One, just because you can see the details of the smaller data reductions when you separate them. Two, as I mentioned before, the size of the data that can be transferred is up to 256 bytes in a single message. So here you're seeing the effect of pipeline, the effect of pipelining messages. And as a matter of fact, around the speed up for 2K versus 8, the speed up in using hardware for 2K is actually close to a factor of 4 as compared whereas for the 8-byte reduction, if you remember, was on the order of 2.5, a factor of 2.5. So there is benefit. There is actually a big benefit to using it, even for medium-sized messages, to accelerate the reduction time. The other thing you can see from the fact that it's using, in this case, I believe it was using 16 fragments. I think that, actually I can't remember if it was 8 or 16, but you can see that the device is handling multiple outstanding fragments well. A different way to look at a different set of results here showing latency of small data reductions, 8, 32, and 128 bytes. All these measurements are taken at 128 nodes. But here what varies is the number of processes on the end node. So you divide your computation into an on-host portion. So for an all-reduce, for example, it would be a reduction, an off-host portion, which would be the sharp portion, and then the on-host portion for a broadcast or something like that to spread the result. And so these measurements here show for one process per node, 2 processes per node, 27 and 28. And the main feature here, so a couple things that we observe here. First of all, the difference between using sharp and not using sharp is similar as you go as a function of processes per node. The other thing to notice here is the portion of the cost for the on-host portion is becoming very noticeable compared to the off-host portion. So that's a next problem that needs to be addressed. The same result, just for larger data. Due to time, let's not dwell on it anymore. And in terms of impact on applications, as I said, the benefit to application depends on first of all if they're using the operations that are optimized in the first place, and two, the degree to which load imbalance is an issue with a given application. And here there's some measured data for reiterating some of the data for in a slightly different format on the advantages of using sharp versus not using sharp. The next thing I want to talk about, I think I have about 10 more minutes, is tag matching, specifically MPI tag matching. As I mentioned before, this is a technology that was developed as part of the Coral program, just like sharp. And the goal here is to address issues that are endpoint issues, so specifically point-to-point communication. And point-to-point communication for MPI, which is still by far the widest used communication protocol in HPC. So a bit, I don't know what the background of the audience is, so just a few terms so that we're on the same page and sort of understand from a technical perspective what's going on here. We have the sender, which is obvious. It sends data to a target. The receiver is the one that receives the data. The data can at the end point either be expected by the receiver. So you talk about expected receives, or it can be data to the receiver that the receiver doesn't know yet that they'll need. So that's called an unexpected receive. When you send the data this is an implementation choice. Most MPI implementations implement basically two types of algorithms for sending the data with the purpose of conserving the amount of temporary buffers that the MPI implementation needs to use, and therefore the application can't use. There are eager sends where the data is sent immediately, all the data and the matching envelope. And then there's a Rendezvous Protocol where you send just the matching envelope and perhaps some data along with it. And later on, after the tag matching occurs, the rest of the data is brought from the sender to the receiver in some mode. a bit about MPI tag matching. So there are 4 parameters used in MPI tag matching. There's the tag, there's the communicator, and there's the destination of the data and the source. So all these need to match for data to that envelope that's sent by the sender needs to match the envelope that's posted by the receiver for the match to occur. On the receive side, the receiver can say, "I'll take any tag," or it can also say, "I'll take any source," but the communicator can't be wildcarded, and the destination is usually implicit. The other thing about that makes MPI tag matching challenging is that sending has to be ordered. Tag matching has to be ordered. So if you send the sender sends 2 successive tags with the same signature, the receiver has to match them in the order to which they were sent. So that's really this requirement is what makes MPI tag matching difficult to implement from a resource perspective. It's a simple idea, but from a performance and a resource perspective, this is a challenge of doing MPI tag matching. So typically, logically, one thinks of a critical region to do the tag matching. You have 2 ways that data that one can enter tag matching. From the application side of things, on the receiver, one can post a receive saying, "I'm ready to receive the message," or data can come from another process, and the challenge here is matching these, and the requirement here to avoid race conditions and get correct matching is that you have to either process a posted receive or a message that's coming in from the network. You can't do both of them. If you do, you run into race conditions and efficiency reasons and something like things like that. So the hardware needs to deal with that. So I won't go there. So just a picture of what the eager protocol is and Rendezvous is. I already explained them in words. Eager, the data is sent directly. There's one path. The data goes from the requester to the responder, sender to receiver. If you have Rendezvous, you have the match header being sent, and then once the appropriate receive has been matched, you have some sort of way of getting the data. This is one way to do it with a read but this isn't really an implementation detail. So now to what's probably the most interesting thing here is, first of all, in the current implementation, only expected messages are handled by are matched by the hardware. So data comes in from the network. If the hardware has the expected receive posted to the network, it will do the match, deliver the data directly to the correct destination without having to go to any sort of temporary buffers. If the hardware can't find a match, whether it's because the posted receive is on the part of the list that's actually sitting up in software and not in hardware because of resource constraints, it passes that posted receive up to the software level, and software handles it from there. So all unexpected messages are handled by software, which actually turns out to have several advantages to it in multi-device type of environments. The other thing that is offloaded is the Rendezvous Protocol. So one of the big reasons not the only reason, but a big reason to implement the Rendezvous Protocol in hardware is because it lets you do matching as the application is computing. And more important from that is if your message is large, you can actually deliver the data directly to the destination as the computation progresses, and provide a way for overlapping computation and communication. This is really a big driver for this. A few other characteristics. The hardware can actually at some point say, I'm not going to handle tag matching anymore, hand things back up to software. It's actually all software initiated, but that's a detail. And it also has full support for MPI, the MPI spec. So it supports probe, iProbe, mProbe, and the non-blocking mProbe, as well as cancel. So a bit more about this. So one of the motivations to let the software handle the unexpected messages rather than putting it to the hardware is because software only tries to do matching when new posted receives are come in, and so there's not an issue of progress here. There's the application has to be active to put to post a new receive. That is, it has to be a request that comes from the application itself, and so there's no time lag. You're no waiting around for some sort of time slot to progress those expected messages. Those posted receives. So those new receives can be matched immediately against the unexpected message very efficiently, unexpected message list. And so this is actually an implementation that not only offloads the capability, but also will help speed up overall tag matching. So the challenge here is, again, the speed of matching on the card versus the speed of matching at a processor that tends to run at higher frequencies. So a few very early performance results. This feature is still in the process of being fully released. So looking a bit at latencies of matching here, the latencies for 1K through 16K listed. And we can see some blue is the latency of the hardware-based tag matching, and brown is the latency of the software-based tag matching. We can see at 16K there's a significant improvement in latency. Really, the major reason, at least in the apps that we've looked at, the major reason for this speed up is because you save memory copies. So if you're familiar, again, with MPI implementations, is typically there's use of temporary buffers for the initial data that comes, and so you pay a CPU initiated latency cost for copying the memory. Here with the hardware tag matching, the hardware delivers the data directly to the correct destination. In terms of the ability to overlap tag matching with other computation, since the hardware is designed to be offloaded and not use CPU resources, you can see that it has much better performance offloading characteristics than software-based approaches. And the problem here, of course, is the whole issue of progress. How do you progress when you're trying to also do computation? And so this addresses that. Last slide again. A lot of what we're doing, or all of what we're doing, is to improve application performance. I gave a couple of examples of some very recent technologies that are aimed to do precisely that. And here's some average numbers for speedups, total speedups for some applications in weather, automotive chemistry, and other areas. So that's it. Any questions?